So let's do an example of with quadratics so we can kind of further explore this topic. So example. We're going to use a really similar regression than the one that we used before when we were looking at beta coefficients. So let's say now we're interested in the log of price here. We're not going to have beta coefficients, we're just going to have kind of regular coefficients. So let's say we're going to take the lateral log of nitrous oxide. They get some nonlinearity now, so it's percent changes, where it's kind of, this is going to capture the elasticity between these two variables. Beta 2, let's say that, again, the log of distance, that's how we're going to think about nonlinearities. And now let's say we have beta 3 times rooms plus beta 4 times rooms squared plus beta 5 times the student-teacher ratio. And so here's this quadratic, right? Because we have rooms and rooms squared, equivalent of x1 and x1 squared, or x3 and x3 squared, whatever you want to call it. So let's first think about what the marginal effect of adding another room is. Marginal effect of a room on, let's just make it on the natural log of price. So don't have to worry too much about percentage changes here, because we're just thinking about this dependent variable. So the change in the natural log of price over the change in rooms. We're going to take the derivative of this right-hand side with respect to rooms. And so if we do that, we get beta 3 plus 2 times beta 4 times rooms. So again, the marginal effect is going to depend on the number of rooms. So if we have 10 rooms and we add an 11th, that marginal effect of adding that room is going to be different if we just have 4 rooms and add a 5th room. Okay, so now let's say we estimate the model. So this is like the theoretical marginal effects. So let's say we estimate it. I'm not going to write out all the standard errors and everything like that, but let's just at least write out the coefficients. So hat, because it's estimated, let's say this is the intercept, minus 0.902 times the log of nitrous oxide, minus 0.087 times the log of distance, I think that's to an incinerator, or community center or something like that, minus 545 times the number of rooms, plus 0.062 times rooms squared. Somehow we have a minus for the student-teacher ratio, but minus 0.48 times the student-teacher ratio. I'm not going to write all the standard errors in because we're not really going to talk about them right now. And so let's now think about this relationship. So I mean, if we wanted to see if we should have a linear versus quadratic relationship, then we could do a t-test on this parameter here, right? If we had the standard error, we could just do calculate a simple t ratio and see if we should get rid of this rooms variable or not. So that might be the first thing. But let's say we instead want to understand this relationship. Well, now the marginal effect, so the estimated effect on a change in rooms equals minus 0.545 plus 2 times 0.062 times rooms. So this is the estimated marginal effect. And now we can let's erase this and draw out this relationship. So this first one is a negative, the second one is a positive, and this negative, an absolute value, this first one is larger than this second one in absolute value, right? So let's draw out this relationship and think about, calculating maybe an important point along that. So let's graph out this relationship. We got some estimated coefficients, and we can think about what the relationship between the log of price, holding everything else constant except for rooms. We're going to vary the rooms. So it's going to maybe start at 13.39, since that was the intercept. And remember that our coefficients, I should rewrite them just so we have them. Remember the marginal effect, so the marginal effect, so the change in the log of price, predicted one, over the change in rooms, was equal to, it was negative 0.545 plus 2 times 0.062 times rooms. Oops, just rooms. Right, this was our coefficient. This was our beta hat rooms here, and this was our beta hat rooms squared. Okay, so let's think about what that relationship looks like. Well, when rooms are 0, there's kind of, there's no total effect, but there's a marginal effect from going to 0 to 1 rooms. And so if we plug in 1 here, we can see the marginal effect of going to 1 room, right? And so put a 1 here, you could calculate this out, and you'll see it's a negative number, right? Because this first term is going to dominate the second term. Since it's, in absolute value, it's so much larger. And so what we're going to see is that we have this kind of relationship between rooms and the estimated effect of rooms on houses. So this is kind of like the total effect, and the derivative is like the marginal effect, right? And so, here's this relationship. It's going to go down for a while, and then eventually it's going to kick back up. As soon as we get to a certain number of rooms, the second term is going to overpower the first one. We just can see what that number is, right? So if we want to see, we're going to see that this is minimized because of the shape of it when the marginal effect equals 0, right? So if we figure out 1 minus 0.545 plus 2 times 0.062 times rooms, we want to figure out where that equals 0. And we're solving for this rooms here, right? This is what we're solving for. So we just need to rearrange that. So we can move 2 times 0.062 times rooms equals 0.545 in rooms. So this is, let's say the minimization, we'll put a star on it to show that's the minimizing this. Take the second derivative to see that it's a minimized. Rooms equals, divided by this, so 0.545 divided by 2 times 0.062, and I luckily have that written down here, and it's 4.4. And so here, through this math over there, we're figuring out where this derivative, this function equals 0. And that's at 4.4. So let's think about what that means in this scenario with this regression. Well, it means as we add, if we have less than 4.4 rooms in our house, and we add rooms, we're actually decreasing the price of our house by adding rooms. Well, that seems a little bit weird, but we'll talk about that in a minute, or we can talk about that in a couple seconds actually. But then eventually, as soon as we have more than 4.4 rooms in our house, then adding another room to our house is increasing the price. And you see that it's getting increasing returns the more and more rooms that we have. So the marginal effect of adding another room is more the larger the number of rooms we have in the house after we're past this 4.4. Now, it's a weird relationship, right? Well, if we actually looked at the sample that the book estimated this by, only 1% of the sample has less than 4 rooms. So it's, there's not that many observations actually down here. It's kind of picking up the second part, this kind of increasing returns here, rather than kind of this part. There's just not many observations with less than, not many houses with less than 4 rooms in it. So we're just not getting a good estimate of what's happening in these low levels of rooms. Okay, so hopefully that kind of, this actual example helps you understand what we're trying to do with quadratics. We can get increasing returns, decreasing returns. Just kind of allows us with some nonlinearities, to put some nonlinearities into the regression. Have the marginal effects depend on the level.